So today, we're going to dive into a truly revolutionary idea from the physicist Hermann Weyl. It's a concept that completely flips our understanding of symmetry on its head. And believe it or not, it's a single thread that ties together ancient art, the structure of crystals, and the most fundamental laws of our universe.
I know, it sounds like a riddle, right? You got a living thing, something made by a person, and this invisible force of nature. I mean, what could possibly unite them? Well, the answer is this hidden principle, almost like a secret code that governs the very structure of reality itself. To really find that connection, we have to start by basically throwing out our old, everyday idea of what symmetry even means. We tend to think of it as, a kind of pleasing harmony or a nice sense of balance. But that definition, it's just not nearly powerful enough for what we're talking about. You see, the classical idea of symmetry was passive, just this vague feeling of harmony. But Weyl's modern idea, it's all about action. It's not about how something looks, but about what you can do to it. We're shifting from a subjective, kind of aesthetic quality to a totally objective mathematical test. This right here is the heart of it all. Weyl called this an automorphism. All it is any transformation that leaves an object unchanged. Just think about rotating a square by 90 degrees. You've definitely done something to it, but it looks exactly the same as when you started. That rotation, that's one of its symmetries. It's so simple, but it is incredibly profound.
So this simple idea of an operation that leaves something unchanged, well, that's the key that unlocks this incredibly powerful mathematical language called group theory. It's literally how we write this secret code for any shape or any pattern you can imagine.
A complete set of all these possible symmetry operations is called a group, and it just has to follow three really simple rules. First, you need a do-nothing option. Second, every action you can do must have an opposite action that undoes it. And third, if you combine any two actions, the result has to also be in your set of actions. That's it. That's the entire grammar of form.
All right, to make this feel a little less abstract, let's use a single shape as our guide for this whole journey, the pentagram. Because if we can understand its symmetry, we're well on our way to understanding the symmetry of almost anything.
Now, what's so fascinating here is that the real essence of a pentagram, it isn't its 5 points or its lines. It's this specific set of 10 operations. There are exactly 5 ways you can rotate it so it looks the same, and there are 5 lines you can flip it across. This complete set of 10 symmetries, which mathematicians call the group D5, is the pentagram's true identity.
Okay, so we've got this abstract mathematical code, D5. And the incredible thing is, once you have this code, you start seeing it pop up absolutely everywhere, unifying parts of our world that seem to have no connection whatsoever. Let's take ancient art. Weyl made this amazing argument that the artists who created these incredibly intricate tiling patterns, like in the Alhambra in Spain, were basically discovering group theory without even realizing it. They were systematically exploring all the possible ways a pattern can repeat itself perfectly across a flat surface.
And here's the kicker. You might think there are infinite ways to do that, right? Well, there aren't. Mathematically, it's been proven that there are only 17 possible wallpaper groups. That means every single repeating pattern you have ever seen in your life, from ancient mosaics to your kitchen wallpaper, belongs to one of these 17 types. That's it.
And this same principle applies to the inorganic world too. That beautiful geometric shape of a crystal, it's not an accident. It is the large-scale, macroscopic expression of the symmetry group that's governing its underlying atomic lattice. The outer form literally reveals the inner law.
And again, just like with the wallpaper, the possibilities aren't infinite, not even close. Group theory proves that there are only 230 possible ways for atoms to arrange themselves into a perfectly repeating crystal. That's a fundamental constraint of the universe, figured out with pure math. It puts a serious limit on the chaos of infinite possibility. And this illustrates such a key division in nature. The fivefold symmetry of our pentagram, that D5 group, is mathematically forbidden in crystals. You just can't make a repeating lattice with it. But in living things, it's everywhere, from flowers to starfish. Even our own bilateral symmetry is just a super simple 2-element group, do nothing and reflect once.
So we've seen how symmetry governs form in art and in nature. But now we're about to take the biggest leap of all, applying this exact same principle to the very laws of physics.
So what happens if the thing that has to look the same after you've done something to it isn't an object in space, but the very fabric of space-time and the physical laws that operate within it. What does that even mean?
This was Weyl's masterstroke. He realized symmetry wasn't just a way to describe things that already exist, it could be a constructive principle. You could insist that the laws of nature must stay the same under certain transformations, and that demand alone could lead you to discover the correct laws of physics, like his incredible theory of gauge invariance.
You know, this whole framework leads to a pretty amazing philosophical payoff. It gives us a rock-solid, mathematical definition for a concept that philosophers have been debating for centuries: objectivity.
And here it is. It's that simple. The objective things are just the things that don't change when your perspective changes. The real stuff is whatever remains invariant when you apply all the possible transformations. What's true for me, and for you, and for some observer flying by in a spaceship, it's whatever survives all of our different points of view.
Einstein's relativity is the perfect example of this. At first, it seemed to destroy objectivity, right? Because suddenly things like length and time became relative to the observer. But Weyl's idea saves it. Sure, length is subjective because it changes depending on your motion. But this other thing, the space-time interval, is objective because it's the same for all observers. Objectivity isn't lost, it's just relocated to a deeper, more fundamental level.
Okay, so all of this has been building to one final, truly breathtaking conclusion. The connection between symmetry and the rules of the universe, well, it isn't a nice metaphor, it's a mathematical identity. The proof for this comes from the brilliant mathematician Noether. Back in 1918, she published a theorem that is, and I'm not exaggerating, one of the most beautiful and important ideas in all of physics. It gives us the explicit mathematical link between symmetry and lawfulness. Think about this. The fact that the laws of physics are the same today as they were yesterday, that's a symmetry in time, and it is mathematically identical to the law of conservation of energy. The fact that the laws are the same here as they are on the other side of the galaxy, a symmetry in space, is the reason momentum is conserved. They are literally two sides of the same coin. Symmetry doesn't just look like a law, it is the law.
And that leaves us with one last, kind of mind-bending thought to chew on. If the deep order and lawfulness of our universe is just an expression of its perfect symmetries, then what are the most interesting, most creative events in the history of the cosmos, from the Big Bang to the origin of life, if not the result of those perfect symmetries at some point being broken?